We usually view space as a rigid stage, an unyielding grid where objects move between fixed points. In Hamiltonian mechanics, however, we move past the physical map and into the abstract realm of phase space. Within this domain, a system is defined by two variables, position, or q, and momentum, or p. Here, q and p function as independent and mathematically equivalent dimensions. This equivalence allows us to redefine the coordinate system entirely. We possess the mathematical freedom to treat momentum as a position, or vice versa, without losing the ability to describe the system. Phase space represents a malleable mathematical environment where coordinates are arbitrary, provided the underlying physics remains preserved. When we shift from old coordinates, q and p, to an entirely new set, capital Q and p, we are performing a canonical transformation. For this shift to be valid, it must leave the fundamental laws of motion undisturbed. To remain canonical, the new variables must perfectly preserve the functional, symmetrical structure of Hamilton's equations. While the equation structure is invariant, the actual Hamiltonian function often changes. When expressed in new coordinates, it becomes a new mathematical function, the Hamiltonian, or k. This transformation allows us to disguise the variables completely, simplifying the mathematics while keeping the predictive laws of motion intact. This presents a calculational problem. How do we guarantee that a coordinate distortion will actually preserve Hamilton's equations? We begin by combining all positions and momenta into a single phase space vector, eta or eta. To manage this vector, we introduce the J matrix, a block matrix built from identity submatrices. These elements allow us to write Hamilton's equations in a unified matrix form. The time derivative of eta equals J times the gradient of the Hamiltonian. We then represent the transformed state, capital Q and P, as a new vector, epsilon. To bridge the old and new vectors, we define the Jacobian matrix, M, as the derivative of our new coordinates with respect to the old ones. Inserting these new variables into the matrix equation allows us to test if the functional form survives the transformation. As we simplify the expression, the gradients and time derivatives fall away, isolating a single requirement. M times J times the transpose of M must equal J. This is the symplectic condition. It is the strict geometric rulebook for phase space. Any transformation matrix that satisfies this equation is canonical. Beyond the abstract algebra, the symplectic condition has a concrete physical meaning in the geometry of phase space. Here, the Jacobian matrix M distorts a parallelogram in the original position momentum plane, mapping it into the new coordinate space. Because of the symplectic condition, the determinant of the matrix M is always 1. This ensures that the total area of the shape is conserved, regardless of how much the transformation stretches or skews the perimeter. This area preservation provides the geometric proof for Liouville's theorem. Canonical transformations can reshape a system's representation, but they perfectly conserve its fundamental information density. While checking matrices works for verification, guessing new variables and testing them against the symplectic condition is inefficient. Solving actual physics problems requires a deterministic method to build valid coordinates from the start. This method begins with Hamilton's principle. For a transformation to hold, the action integral for both the old and new coordinates must be stationary. Variational calculus allows these two integrals to be linked if their underlying functions differ by the total time derivative of an arbitrary function. We define this arbitrary function, g, as the generating function. To function correctly, g must be a function of exactly one old coordinate, one new coordinate, and time. By providing a mix of coordinates to this framework, we can automatically derive a perfectly legal canonical system. There are 4 primary ways to bridge these variables. Type 1, or G1, connects the old position Q with the new position Q. Taking the partial derivatives of G1 produces explicit formulas for both the old and new momenta. Consider the case where G1 is simply the product of the old and new positions. The calculus resolves to show that the new position is the old momentum and the new momentum is the negative old position. This proves the fluidity of phase space. It demonstrates that position and momentum are not rigidly distinct variables, but elements that can be swapped entirely. We can also apply this framework to the smallest possible changes, known as infinitesimal canonical transformations. These microshifts rely on a specific type 2 generator, where G2 equals the product QP plus a small parameter alpha multiplied by a function g. The QP term represents the identity transformation, where nothing changes, while the second term generates a tiny differential deviation. Deriving this generator produces formulas for the microscopic changes in position and momentum. These infinitesimal steps allow us to map a system as it evolves smoothly, suggesting a deep connection to the way physical systems move through time. What happens if we use the system's own energy, the Hamiltonian, as our generator, and a tiny step in time as our parameter? We substitute h and dt into our infinitesimal transformation equations. The equations resolve perfectly back into Hamilton's equations of motion. This reveals that the simple passage of a particle through time is mathematically indistinguishable from an active coordinate transformation. Here, time evolution emerges as a continuous, unfolding canonical transformation of the system onto itself. This provides a complete mathematical framework. The symplectic condition proves geometric legality, generating functions build the pathways, and the Hamiltonian drives the flow. Since their application to complex orbital mechanics in the mid-19th century, these tools have remained the foundation of advanced physics. By proving that coordinates and momenta are entirely fluid and arbitrary, canonical transformations completely liberate mechanics from physical space, providing the mathematical depth required to solve the universe's most complex dynamical systems.